Hey everyone, we're going to spend a few minutes here. It's a really short topic. We're going to go over the simple pendulum, and you guys are probably familiar with a couple different examples of pendulums in use. Mechanical clocks use pendulums. Wrecking balls on a crane would be an example of a pendulum. For the bowlers out there, swinging your arm to try and build potential energy by swinging your arm backwards to lift the ball is in a pendulum motion, and we release that energy when we push the ball down the lane. A metronome is an example of a pendulum, and it's really quite a simple device. It consists of a bob or a mass, and the bob is going to have some mass to it, and it's attached to a string or rod that we would assume has really negligible mass. Now, the length of the pendulum is going to tell us a lot, and it's measured from the pivot point of the pendulum at one end of the string or the rod to the center of the bob or the mass. Now, in the equilibrium position, the string is going to be perpendicular to the ground. So if we had our ground here, the string of the pendulum would be aimed straight down, and we would create a right angle there with the string of the pendulum. Now, the angle the string makes with the equilibrium position is what we call the amplitude, and we measure that as an angle in regards to the equilibrium position. So on the drawing here, our amplitude would be this deviation here from the equilibrium position. We would have a bob on the end of our string here, and this bob will move back and forth depending on the motion of the pendulum. This would be our bob or our mass. Equilibrium, assuming that ground is at the bottom here. Equilibrium position is this position right in the middle. The string can have length L, and that's going to change how this pendulum is going to move. Now, the time required for the displaced pendulum to complete one cycle of motion, so from where the pendulum is released to swing to one side and come back to where it was released, or excuse me, from equilibrium to one side, back to the other, and back to the equilibrium position, so touching both sides opposite the equilibrium position, is called the period. And kind of like impulse, we use a variable t, unrelated to any of the letters in period, to represent the period of the pendulum. So that's basically going to be a period to go from 1 to 2 and back to 3. By the time we get back to 1, this would be our period. So we got to hit from points 1 to 2 to 3 and back to 1 to count for 1 period. The number of cycles that the pendulum is going to complete per unit of time is what we call the frequency. And the frequency we will measure in a lowercase f. And the units for this are hertz, which you've seen a little bit with our Pasco software, or hertz. Now, the equation that we use to determine our period is 1 over, can we do that? Is 1 over our frequency. Or, Another variation we can use here, the period is equal to 2 pi times the radical of the length of the pendulum divided by g, where g is equal to acceleration due to gravity. And we know that value as 9.81 meters per second squared. So gravity is going to have a different effect on that mass, and it's going to cause that period to change. I'll show you an example of this in class next time, so we can see how changing the length or changing gravity or even changing friction will affect the period of the pendulum. Now, the period of the pendulum is independent of the mass of the bob. So by changing that mass, we're not going to change the period of the pendulum. We'd have to look at, as far as changing the pendulum, the length here of the string. By changing the length of the string, we're going to adjust the period. So the period is affected by the length of the string as part of the pendulum and the acceleration due to gravity. These two factors are going to affect how this pendulum is going to swing, how long its period is going to be. And this is represented with G. I'll show you some examples of this tomorrow. Hope you guys have a great day.